Okay, hi everybody, welcome to the second to last pre-recorded lecture, and today I'm going to count trees. Let me remind you what we did last time and what is a tree. A tree is a connected graph without cycles. So an example of a tree. And I mentioned last time that there is a few equivalent characterizations of a tree, and the one, let me just quickly review them as well. So if G is connected, so let's say G is a pair V comma E, let G be connected. And then the following conditions are equivalent. The first one is that G is a tree. And there is a few more. One is path uniqueness, which is that for any two vertices x and y, G contains a unique path from x to y. So, and here the difference between paths and walks is essential. There could be, if you have two vertices x and y, there could be many different walks from x to y. I don't know, whatever. But there is only one path for any two vertices. And the third condition is that G is minimal connected, which is that removing any edge from G gives a disconnected graph. And finally, the last condition is the Euler's formula. Which is just that the number of vertices is number of edges plus 1. So that formula plus connectedness means you have a tree. So how do we count? So the question is, how many different trees? And well, so today I promised to do graph isomorphism, but actually I don't need that today as well. So let me just say that if you have two graphs, G1, V1, VE1, and G2, V2, E2, and then G1 is equal to G2 if and only if they have identical sets of vertices and identical sets of edges. So in other words, no matter how you draw, I don't know, I can draw one graph maybe like this, 1, 2, 3, 4, and I can draw another graph like this, 1, 2, 3, 4. Now these two graphs are the same. It doesn't matter how I draw them in the plane, just that the set of vertices is 1, 2, 3, 4, and the set of edges is 1, 2, 2, 3, 3, 4, and 1, 4. So, and that's the notion of equality. If they are not equal, otherwise call them different. So what I'm going to try to do today is I want to try to count how many different trees with vertex set bracket n. And yeah, that's what we tried to do last time. So last time we computed an example for n equals to 2. There was one tree which looked like this. And there was an example for n equals to 3, where we had 3 trees. One, two, three, 1, 2, 3, 1, 2, 3, and so today let me try to continue. I think it is a good idea to compute n equals to 4 and n equals to 5 as well. So for n equals to 4, if you forget the labels, then there is basically 2 types of trees. There's either a path or a star like this. That's without the labels. And now you have to count them as labeled, right? Because I mean all these trees are all a path, so they're sort of isomorphic as graphs, but they have different labelings. So how do I count how many labelings for each of these trees? Well, for the path, it's very easy, right? So you can count, you can label them in any way you want, right? So maybe you can label it W1, W2, all the way up to Wn for any permutation W in a SAN, but then if you reflect the path, then the labeling is going to stay the same. So, well, the tree as labeled tree is going to stay the same. So for example, 1, 2, 3 is the same as if I put 1, 2, 3 like this, then I'm going to get the same labeled tree, just drawn in a different way. So the point is that every path gives me n factorial over 2 options. Well, n factorial over 2 different trees. Where you have to divide by 2 because of the reflection of the path. And similarly here, you can see that all the leaves, well, all these kind of branches of my star are sort of, I can permute them without changing the tree. So the only special vertex is the one in the middle. In particular, there's n options for this. N trees. In other words, I can label this by 3, and then doesn't matter 1, 2, 4. It doesn't matter in which order 1, 2, and 4 come. Once I choose the 3 here, the tree is uniquely determined. So in particular, the answer is. So the answer is I get n factorial, so 24 over 2 plus 4, which is 16 trees. 16 trees. Previously we had 3, and previously we had 1. So these are not Catalan numbers, not n factorial, not Fibonacci. Okay, so what is it? Yeah, let's try another one. Let's try another example, because now we can count trees in a smart way. Example, n equals to 5. And that's about as high as I can go. So for n equals to 5, first of all, I have to list all unlabeled trees. And that is, so let's see, there's always the path and the star. 1, 2, 3, 4, 5, and star looks like this. And the path gives me n factorial over 2 trees. The star gives me n trees. But there's one more kind of tree, which is, let's see if I can, if I do this, this, and this, and then, right, there's also a tree that looks like this. And there's no more. If you try to draw, well, first of all, how do you check that there is no more? If the degree of each vertex is at most 2, then your tree has to be a path. It has to be a path. So in particular, there is only one tree with degrees of all vertices. A degree of vertex is the number of neighbors of your vertex. So if every vertex has at most 2 neighbors, then it has to be a path. Now, if some vertex has at least three neighbors, then you already found 3 vertices out of 4 possible vertices. Right? So you try to see in how many ways can you add another vertex to this tree here to make it still be a tree. And the answer is you either connect it to the 3 to the vertex in the middle, or to some of the leaves. Anyways, and you get one of these 2 trees. And so how do you count how many trees does this how many labeled trees does this guy give us? And the answer is you can still label. You can start with any permutation: W1, W2, W3, W4, W5, and basically the vertices 3, 4, and 5 are special, right? But 1 and 2 can be permuted with each other. So that one also actually gives us n factorial over 2 trees. So in other words, yeah, for any 2 permutations, they give us the same labeled tree if and only if they are obtained by swapping the first 2 entries. So the answer is well, n factorial over 2 plus n factorial over 2, which is 120 plus 5, so that's 125 trees. And now this becomes suggestive. 1, 3, 16, 25. Let's make a table. Number of trees. N is equal to, I guess, 2, 3, 4, and 5. 1, 3, 16, 20, 125. Well, yeah, that's the answer is that the number of trees is basically well, let me introduce one notation. Let fat T of n be the set of trees on the vertex set bracket n. Then the claim is that's called Cayley's formula. Cayley formula, which is one of the most beautiful formulas in, I guess, all of combinatorics. The number of different trees on bracket n is, well, the size of this fat T of n is equal to n to the n minus 2. So 125 is 5 cubed, 16 is 4 squared, 3 is 3 to the first, and 1 is 2 to the 0. Which, yeah, so by the way, if you, let me give you a slight detour. So there is, if you want to, this formula has many different proofs, and I'm going to give you at least 2, possibly 3. And if you want to know more, there is a book called Eigner and Ziegler are the authors, and the book is called Proofs from the Book. Yeah. So, and anyway, the idea is that there was some mathematician called Paul Erdős. Which is one of the most productive mathematician of the 20th century. He was a combinatorialist, and he believed that that God has a certain book where he has all the best stuff. Right? All the most beautiful proofs are in that book. So Eigner and Ziegler published a book where they collected some of the most beautiful proofs, and they called it proofs from the book. And yeah, so this, according to them, the book contains 4 proofs of the Cayley formula. So if you want to know more about this formula and some other interesting, some other beautiful things, then maybe you would want to look it up. Yeah, and also if you want to know more about this guy, yeah, there's an interesting Wikipedia page you can read about Paul Erdős if you don't know who he is. Yeah, but anyways, that's the detour. Let me now try to explain the first proof. And the first proof is going to be, I mean, it's a nice double counting trick. But yeah, later I'm going to give you generalizations of this theorem, and for that I'm going to need another proof. But for now, I think that's the easiest proof, which is still sort of tricky. So what to do is so the goal is to show that the number of trees on n vertices is n to the n minus 2, which I can rewrite as I can multiply both sides by n squared. N squared times the number of trees is equal to n to the n. And here, now both of these sides are suggestive in that you can come up with a combinatorial interpretation for each side. I mean, you could do this for here as well, but it's easier here. So the left-hand side counts what? It counts, well, you choose a tree and then a pair of vertices. So let me call that doubly rooted trees. Counts doubly rooted trees, which just by definition are triples TLR, where T is a tree, so T is a tree on bracket n, and L and R are just arbitrary indices, which I'm going to think of as vertices of my tree. Remember, the vertices of the tree are labeled, so let's see if I have, do I have a drawing of the tree? Okay. So you have some labeled tree. 1, 2, 3, 4, 5, 6, 7. And then you just choose arbitrary to, maybe they can be the same indices or different. So maybe you say that this is L, and maybe, or yeah, maybe this is R. Doesn't matter. You just an arbitrary triple like that is a doubly rooted tree. So the number of such trees is the left-hand side. Now, what is the right-hand side? The right-hand side is the number of arbitrary functions from bracket n to itself. The right-hand side counts functions from bracket n to bracket n. Maybe, should I call these? Yeah, maybe f from bracket n to bracket n. So how do you convert a doubly rooted tree into a function? Or how do you convert a function into a doubly rooted tree? So let me do the other way around. So let me try. What I'm going to try to do is I'm going to take any such function f. It doesn't have to be injective or surjective or bijective, just arbitrary, sequence of n numbers. And then I'm going to try to draw it as a directed graph. Draw it as a directed graph. So maybe I should try an example. Maybe let's say 1, 2, 3, 4, 5, 6, 7, 8. Maybe my function sends 1 to 6, 2 to 6, 3 to 1, 4 to 6, 5 to 3, 6 to 6, 2 and 2. Yeah, maybe something like this. Then I draw it as a directed graph. So 1 goes to 6, 2 goes to 6, 3 goes to 1, 4 goes to 6, 5 goes to 3, 6 goes to 6, and 7 goes to 2, and 8 goes to 2. Yeah, maybe perhaps that's not a good example. So maybe, yeah, let's try another one. Maybe this time, let's see, I want 2 to go to 1, and I want 6 to go to 2. So what's going to happen is that 6 goes to 2, and 2 goes to 1. Yeah, I think this is better, but I mean, regardless, the proof should work for any function I want. Yeah, let me try to move this one out of the way. Yeah. So okay, so I get a picture like this, and question is, well, in general, what is it going to look like in general? In general, there is going to be some. It's not a permutation, right? So in general, you don't get. If I did the same for a permutation, I would get a union of several cycles. But here I get some branches which end up in the cycle. So there are still going to be maybe several cycles of different sizes, but each cycle is going to have some branches coming into that cycle, which is very easy, right? Every vertex can have an arbitrary number of incoming arrows, but only every vertex, each vertex has exactly one outgoing arrow. That's the important part. And in particular, everything is either a cycle or a branch. So, in other words, if you start at any vertex, you can keep applying f. You apply f, 5 goes to 3, 3 goes to 1, and you can apply it forever. So at some point, you have to start cycling around the same cycle. So in other words, you start at any vertex, then there is a path which at some point arrives at a cycle. Yeah. So, and let me now try to make it rigorous. So let me introduce a set C subset bracket n be the set of vertices which belong to a cycle of f, right, which belong to at least one cycle of the resulting directed graph. And in particular, if I restrict myself to those cycles, if I only look at the cycles, then I get sort of a permutation of C. So here in this case, C is equal to 1 to 6. That's the set of vertices on which I have a cycle. And if I restrict, so I can restrict F to C. And then F to C is the map from C to C. It is a bijection, because every vertex has one incoming arrow and one outgoing arrow. So it's a bijection. And or a permutation of C. So in particular, I can try to write it in two-line notation. write it in two-line notation, which so what I'm gonna do is I'm gonna write the top row. Yeah, I'm just gonna note it by A, B, C all the way up to Z. These are elements of C in increasing order. And then I'm gonna write the bottom row just f of A, f of B, all the way up to f of Z. So here C is the set of A, B. Yeah, I could have just denoted them C1, C2, etc. Yeah. Anyways, the point is that I can write the restriction f to c in two-line notation in this form. So for example, for my write-in example, the restriction of f to c is, what is it? So I write the top row in increasing order, and then 1 goes to 6, 6 goes to 2, and 2 goes to 1. And yeah, so far I'm doing something very natural, right? And now I'm going to use it to construct the doubly, well, I want to arrive at a doubly rooted tree. So I want to explain what is T, what is L, and what is R. And okay, let's try to explain that. So first of all, well, I want to set L to be f of A and R to be f of Z. So yeah, let me redefine, because I don't like this. Let's say A, B, and Z are C1, C2, all the way up to CK. F of C1, F of C2, all the way up to F of CK. C1, and I'm going to assume that C1 is less than C2, less than etc., less than CK. So in this case, L is f of C1 and R is f of CK, where K is the size of C. Okay, so far I have already, out of my triple TLR, I already know L and I know R. And finally, how to define T? Well, I'm going to do it as follows. And well, here's the idea. First, the first thing you do is you look at the bottom row of this two-line array, and you just draw a path from f of c1 to f of c2 to f of, yeah. So start with draw a path from connecting f of c1, right? It's a vertex, so you connect it to f of c2, etc., all the way up to f of ck. And that path is gonna be some part of your tree, right? But I have not used all vertices, but I have only used a subset of vertices, which is C. And now I only have to, so in other words, there's a whole bunch of vertices. There's a whole bunch of vertices left in my tree which are not connected to anything, right? So if I is not in C, then so far I have an isolated vertex in my tree. And now what I'm going to do is, for each I not in C, I'm going to draw an edge connecting I to f of I. So let us try to copy the example I had here. Example. So if f is this and c is 1, 2, 6, right? Then I look at the bottom row and I see 6, 1, 2. All right, so I draw a path. 6, 1, 2, and I just connect them in this order. And also remember that L is f of c1 and R is f of ck. So L, this guy is L, and this guy is R. So yeah. Now, the second step is for each I not in C. So let's see which i's. C is 1, 2, 6. 1, 2, 6. That is C. And the rest is not in C. So I have all these vertices. 3 is connected to 1. And 4 should be connected to 6. And 5 should be connected to 3. And 7 should be connected to 2. And 8 should also be connected to 2. And I get a tree. So T is this tree here. So well, I have to prove a few things. Right? I have to show that it's a tree. And I have to show that this is a bijection. So that's going to be 2 claims. Claim number 1 is that the resultant triple TLR is a doubly rooted tree. Okay, how do I prove it? Well, I mean, it's the only thing I have to prove is that T is a tree, because on L and R I had no restrictions, just arbitrary pair of indices. But to prove that T is a tree, first T has n minus 1 edges. And why is that? Because, well, let's look at the 2 steps. If you draw a path through the vertex of C, so the path from f of c1, f of c2, all the way up to f of ck has k minus 1 vertices, k minus 1 edges, sorry. And for each I not in C, I get 1 more edge, which connects I to f of I. So in total I get n minus k edges. So the total number of edges is n minus 1. And that's one claim, and the other claim is that T is connected. And the reason for that is also very simple. First of all, the path f of c1, f of c2, etc., f of ck is connected because it's a path connected. And the other point is that for each I not in C, you have a path from I to f of I to f of I to etc., which in the directed graph corresponded to 5 goes to 3, 5 goes to 3, goes to 1, and at some point you end up in a cycle. Even though you started outside a cycle, at some point you arrive at a cycle. So 5 goes to 3 goes to 1, and in the tree we see that 5 is connected to 3, which is connected to 1, and 1 lies on the path from L to R. So the claim is that the path from I to f of I to f of I eventually terminates at the path from L to R, where L is, this is L and this is R. Okay, so every vertex can be connected to the path from L to R, which is also connected. So the whole graph is connected. So, and thus T is a tree, which proves the first claim. Now I'm still not done because I have to show the second claim, which is that this is a bijection. Claim number 2 is that this map, f goes to T, is a bijection from bracket n to the n to, the set of doubly rooted trees. So in other words, I need to reconstruct f from the triple. So proof, given a triple T L R, need to recover f and show that it's recovered uniquely. And okay, so remember we had all these conditions. There was I have already used the Euler's formula, right? The Euler's formula was used here, that T has n-1 edges, and now I'm also going to use path uniqueness. So I'm going to remember that in the tree, between any two vertices, there's exactly one path. So in particular, T contains a unique path from L to R, which, so in other words, the one-line notation of the permutation f. So C, and so this recovers C and the one-line notation of the permutation f. The restriction of f to C is a permutation of C. So perhaps I can try some other. I can draw a random tree. And then I label 1, 2, 3, 4, 5, 6, 7. So I choose maybe L is the 4 and R. Well, let's even try R. Maybe R should be this vertex here. This is R. So I look at my path. There's a unique path from L to R. And I see from here that the cycle C, the set C is 2, 4, and the restriction of f to C is 2, 4. In the top row they are increasing, in the bottom row they are in the order they appear in the path from L to R. 4, 2. That's how you recover f sub C, f restricted to C from this triple. And the only thing I have to recover is the restriction of f to all the elements which are not in a cycle. And by construction, for those for those vertices, the way I chose the edges was for every vertex. For every other vertex, there's an edge. there could be many edges, right? So maybe I should draw another one. Maybe let's say there is a 9, 1, 2, 3, or maybe there is a 4 as well. 4, 5, 6, 7, 8. Yeah, okay. Maybe there is also an 8, something like this. So still, for any vertex, there are several edges. So how do you know which one is f of I? And the answer is that there's a unique edge that points in the direction of the path. So in other words, there's a I mentioned that there's for any two vertices there is a unique path, but also there's a unique path from a vertex to a given path. So and that, I guess, is an exercise. So for each I not in C, T contains a unique path from I to C. Unique let's say shortest path. So it has to terminate at C, and no other vertex should belong to C. There is a unique shortest path like this, and so for 8, this path looks like this. I terminate at 2 because I have to terminate at the vertex of C without using any other vertex of C. Yeah. So taking the unique shortest path from I to C, and so let f of I be the next vertex after I on this path. And that allows me to reconstruct the rest of f. So maybe here I should let me try an example. F is 1, 2, 3, 4, 5, 6, 7, 8, 9. I already know that 2 goes to 4, 4 goes to 2. That's the cycle. And these two elements belong to C. And then for the rest, well, 1 goes to 4, and 7 goes to 4, because 1 goes to 4, 7 goes to 4, and 3 and 5 goes to 2. And now here's the tricky part. 6 goes to 2, 9 goes to 6, 6 goes to 2, 9 goes to 6, and, well, wait, hold on, there's 2 4s, all right. Okay, let me erase one of the 4s. And 8 goes to 9, finally. So I have reconstructed the whole F uniquely from just looking at this picture. And that's so yeah, clearly the two maps are inverses of each other. So that proves the second claim and finishes the whole proof of this Cayley formula. Yeah. So, which again, the proof is just double counting, which is, I guess the proof itself, the construction. If you didn't follow the construction, just try to draw a random tree and then try to reconstruct F out of it, or vice versa, and you'll see that it's all pretty straightforward once you kind of get, once you are skilled at applying these two algorithms. Basically, it's all can be programmed very easily. Okay, now let me try to generalize it slightly, and I'm going to continue next time on Wednesday. But for now, let me try to at least give you a at least try to compute some examples of generalization of Cayley's formula, and that's going to be, I'm going to take the degrees of the vertices into account. So by definition, if you have a graph G, if G is a graph and V is a vertex, then the degree D sub V, which sometimes I'm going to specify the graph, sometimes I won't, so denoted by D sub V, is just the number of neighbors of V in G. So the number of edges which are incident to V in G. In particular, a leaf is a vertex of degree 1. So one fact which you probably know about degrees of vertices, and a very simple lemma, is that it's called the handshake lemma. It tells you that if you just take the sum over all degrees, so for any graph G, the sum over all vertices of their degrees is equal to twice the number of edges. And the proof is very simple. It's basically on the left hand side, counts each edge twice. Because for each endpoint of your edge, it's counted once for each of the two vertices. Right, so for example, maybe if I draw a graph like this, the degrees are 1, 1, 1, and 3, right, in some order, and so 1 plus 1 plus 1 plus 3 is equal to 6, and the number of edges is equal to 3, which is twice as 6 divided by 2. And well, that's not the interesting part about degrees. Here's the interesting part. Let me introduce the following function. So let me fix n, some integer, and then define, what I'm going to try to define is a polynomial, f sub n of x1, x2, all the way up to xn. It's a polynomial in n variables. And by definition, it's the sum over all trees in the fat T of n, and that's the set of trees, of x1 to the degree, right? These trees are on vertex set bracket n. So I can define the degree of vertex 1 in T, 2, etc. So d1 in T times x2 to the d2 of T, etc. times xn to the dn of T. And I guess for the rest of today, I'm just going to compute some examples. So let's say I start with n equals to 2. Then my tree looks like this, 1 and 2. So f sub n of, well, f sub 2 of x1 comma x2 is equal to x1 times x2. Now let's try the next one. Example, n equals to 3. I had 3 different trees. 1, 2, 3, 1, 2, 3, 1, 2, 3. And each of them, first of all degrees are at least 1. Right? The tree is connected, so each vertex has to have a degree at least 1. And here, for each of these trees, there is one vertex that has degree 2. So f sub 3 of x1, x2, x3 is equal to x1, x2, x3 times x1 plus x2 plus x3. which, by the way, this is a homogeneous polynomial. Right? The total degree of all vertices is, the total degree of all variables is 2n always. So this guy is of degree 4, for example. Wait, hold on, it's 2n minus 2, right? The number of edges is n minus 1, so you multiply it by 2 and you get the total degree of all variables. But okay, let's try, let's see if I can do another one. N equals to 4. And so there was 2 types of trees. One that looks like a path and another one that looks like a star. And you know, you can have any and I'm gonna try to write down f sub 4 of x1, x2, x3, x4, which so here is the clever way to do this. First of all, it's going to be divisible by x1, x2, x3, x4. And then what's going to be left is, first of all, any pair of vertices appears exactly once as these 2 vertices. Well, or exactly twice. So if I want, maybe I want to put 1 and 3 here, and then the 2 labeled trees are either 2, 4, or I could do 2 here and 4 here. I'm going to get 2 labeled trees with 1 and 3 in the middle. So yeah, I can swap 2 and 4, and I'm going to get 2 different trees. So in particular, I get 2x, well, I get the sum of, for over I less than j, of 2xi xj. Right, because 1 and 3 here have degree 2, but I have already divided by, so they are going to contribute x1, x3 twice to this sum. That's the first tree. It's going to give me this sum here. And there is going to be the second sum for the second tree. And the second tree, as you remember, I choose the label of this vertex, maybe 3, and then the rest is uniquely determined. It doesn't matter in which order I put 1, 2, and 4. So, and this is going to give me xi squared. The sum over I in n, xi squared. I mean, it's going to give me xi cubed, but after dividing by this, I'm going to get the sum of xi squared. And the answer turns out to factor. Right? This sum here is a product. Well, it's a perfect square. x1, x2, x3, x4 times x1 plus x2 plus x3 bracket n plus x4 to the second power. So there is a nice pattern, as you see, looking here and here and here. There is again something in the power of n minus 2. Anyways, it's a, next time I'm going to explain what this is in general. And so far I'm going to stop. Everybody have a nice weekend, and I'll see you all on Wednesday.